Hello, everyone. I'm very glad to present this vision paper in WORDS21 workshop. My name is Xiaoyi Lu. I'm an assistant professor at the University of California, Merced. This paper was written by myself and my PhD student, Arjun Kashyap. So in this vision paper, we are trying to present our vision in designing next generation of loadable and migratable microservices on disaggregated architectures. So this is the outline of the talk. Let me first briefly introduce the background of this work. So first of all, as we know, microservices are becoming the new paradigm in cloud computing. The microservice architecture decouples monolithic applications to loosely coupled microservices, which is gaining traction in large data centers these days. Each microservice just performs a specific task, which can be independently deployed and scaled. Big cloud providers have already started adopting the microservice application model like AWS Lambda, Azure Functions, and Google Cloud Functions. On the other hand, disaggregated data center architecture splits the center tier into independent resource pools, such as compute and the storage pool. And the computing nodes or devices in these pools can communicate with each other over fast interconnects. Disaggregated data center architecture can reduce total cost by independent optimization and resource scaling. The benefits of running microservices on such type of architecture include we can exploit the new emerging hardware like remote computational devices for microservices and increasing performance, energy efficiency, scalability, and QoS support of microservices. With this new trends, we believe that there's a high time to think about what should be next generation distributed microservice architecture looks like and what kind of advanced designs we should propose in the community. As I mentioned before, we envision the next generation disaggregated data center architectures to comprise of more and more general purpose and specialized devices, such as persistent memory, computational persistent memory, NVMe SSDs, and CSDs, or RDMA-enabled networks such as InfiniBand and Rocky, and different kinds of multi-core medical chips, including CPU, GPU, DPU, ARM-based CPUs, ASICs, FPGAs, and so on. So future microservice systems should allow microservices and the serverless applications to leverage this new data center architecture and the available capabilities to further improve the performance, scalability, energy efficiency, QoS, productivity, and so on. So to fully exploit all these disaggregated devices, we have to reduce the data movement by pushing or offloading a certain amount of computing in microservices or hover microservices near these computational devices, which means microservices need to be offloaded on disaggregated resources. As shown in the left side figure, we included three different microservices in this figure, M1, M2, and 3. These are microservices that were initially running on compute nodes and get offloaded to computational devices to reduce data movement and achieve high performance, energy efficiency, and load balancing, and other benefits. Later on, microservices might need to be rebalanced and migrated to other remote resources. For instance, as shown in the figure, at some point, M1 or M3 microservices may get migrated to CPM devices from ARM-based CSD platforms to get a better performance, energy efficiency, and load balancing. We envision that many applications can benefit from offloadable and migratable microservice architectures on disaggregated data centers, such as machine learning pipelines, database services, storage services, and so on. So then let's take a look what kind of challenges are associated with this offloadable and migratable microservice concepts. So to achieve the goals of offloadable and migratable microservice or serverless functions, we identify several research challenges here. So first of all, we should think about how we can design effective and efficient runtime systems for microservices and serverless functions that can leverage the novel features of next generation data center hardware. Second, how to offload and migrate the entire microservice or a portion of it to computational devices in an energy efficient and QoS-aware manner. Third, how can we co-design with applications and microservice platforms to achieve near native performance while reducing energy consumption? Fourth, how to offload such tasks with minimal code changes to the applications to keep the developer productivity high. And what kind of benefits can be achieved through these new designs? Last but not least, how to benchmark these designs with microservice platforms and applications. So with this, let's take a look at the research roadmap we propose in our paper. So first of all, it is a challenging task to offload an entire or a portion of microservice to heterogeneous compute units in the data center. This is because we need a standardized, generic, and the programmable interface from the underlying hardware layer. Even though this is a difficult research task, but we do see success stories in the community. For instance, RDMA with verbs and NVMe protocols are becoming standardized programmable interfaces for high-speed networks and storage devices. We envision that more and more standardized programmable interface will become available in the future. Second, producing new compute abstractions may be needed because such abstraction can help to solve many issues related with heterogeneity, performance, productivity, and so on. So far, the most common ways to deploy microservices are based on virtual machines or containers. To solve all the challenges we listed earlier, it may be an interesting and open challenge to rethink what could be the best way to design portable compute abstractions for microservices. Third, microservices could run different kinds of workloads, which can be both stateful and stateless workloads. We think that different approaches should be adopted to handle stateful and stateless microservices. We need offload-aware systems, runtimes, and APIs to support them. For example, an offload-aware communication and IO runtime should be able to automatically and transparently select the best protocols for microservice applications based on the capabilities of the device where the microservice are offloaded to. In addition, we need to develop new mechanisms that enable fast live migration of microservices between host to device, device to host, or device to device using different network protocols and interconnects while preserving the performance. Furthermore, we also envision that task-aware offloading is very important, and it should explore designing new metrics and models which could characterize and predict when and on which computational device it would be useful to offload microservices in disaggregated architectures. A good offload strategy, we believe it should decide where to offload and also take into consideration offloading costs versus rewards. Another important perspective we believe is dynamic resource partitioning. Dynamic resource partitioning for offloaded function is another challenge we think. One must ensure that in running microservices or functions on CSDs or CPMs should not impact the performance of their main task, like I/O processing. To achieve this, hardware vendors may need to provide more resources or mechanisms on hardware devices to help system designs. For example, dynamic I/O queues or resource pools can be provided from the hardware layer to achieve better designs. And as these computational devices will run multiple microservices or functions, there should be strong security and isolation guarantees among the ends as present on the host server. Some possible technologies examples include hardware-based data encryption, namespaces, protection domains, and so on. Also, the load balancer, which would analyze the load of all nearby devices, should make offloading decisions based on data locality and the device node. In addition, offloading microservices should occur if running them on competition devices does not violate their QoS guarantees. Another important factor to consider while executing microservices is that how to respect the predefined energy or power budget. So finally, we believe a holistic cross-layer approach is a critical task to tackling the challenges at these different layers. And we envision that the next round of potential innovation will happen in next 5 or 10 years after materialize the research roadmap discussed here. So now let me, after we discuss all these high-level ideas, let's, in my group, we have done some preliminary works to offload different kind of computation or communication to the network or GPUs. So here, let me give a case study, concrete case study about how to design efficient erasure coding service offloading schemes on top of network. So before we discuss our approach, let's have a quick overview of the brief history of erasure coding. As many of us know, maybe in the 1950s, Hamming proposed the first erasure code to ensure reliable communication over unreliable physical channels. Later on, many other erasure codes such as Redstone code, BCH code, and the RDBC code have been proposed to achieve transmission reliability. The successful use of these erasure codes finally caught the attention of researchers in the story community as well. From 1980s to 2000, multiple RAID technologies have been proposed to ensure reliable data storage over inexpensive disks by leveraging erasure codes. Starting from the first decade of the 21st century, due to big data challenges, many systems started to use EC-based alternatives instead of replication to achieve story-efficient fault tolerance. This is particularly important for in-memory storage like key value store services. Many existing distributed storage systems such as HDFS or Ceph have adopted EC-based resilience schemes. To improve the performance of EC, researchers have designed several storage-oriented erasure codes such as ARC code, PPR code, and EC pipe code. In my group, we have proposed 3 designs which are UMREC, TryEC, and InEC. UMREC is trying to support both onload and offload EC coders in a unified approach. And the TryEC and the InEC are designed for offloading EC to smart NICs. In this talk, I will focus on our studies for InEC, which was published in SC20. Other 2 work you can find from the following papers. The original motivation of InEC comes from our observations about the state-of-the-art EC schemes. In this slide, we use 5 representative state-of-the-art EC schemes to explain the observations we have. These 5 schemes include conventional RS code, TryEC code we proposed earlier, and then ARC code, PPR code, and EC pipe code. In most EC schemes, we can usually find networking operations such as send and receive that are used for data transmission. And on the other hand, the most common operations in these EC schemes are a mix of EC computation and networking. For instance, these highlighted nodes in different EC schemes in the green box need to perform EC computation and then send the results to other nodes. And for these nodes highlighted in yellow box, they have to wait for some data first, then conduct EC calculations, and then send the results. We also have some nodes as highlighted in the blue box that need to do some computations on the received data, but don't send the results to other nodes. So they first wait for the data to arrive and then carry out the computations on them. The nodes in the red box just need to perform networking functionality such as send and receive. With all these different state-of-the-art EC schemes, we start thinking that what kind of opportunities and challenges are there for us to further optimize their performance. What we learned here is that EC calculations are tightly coupled with data transmission in this state-of-the-art EC schemes. So we also find that in modern and next-generation data centers, smart NICs with EC capabilities will be a promising approach to design next-generation distributed storage systems. So EC capabilities can be split into 2 categories on network-based EC approach. One is called coherent EC calculation and networking. In this approach, CPU needs to talk with smart NIC for many times to complete EC computation, and data transmission. The other approach is the coherent EC calculation and networking, or we can say coherent network EC. In this approach, CPU can offload EC computation and communication tasks to SmartNIC with one post. And the SmartNIC will automatically execute these tasks one by one without any further CPU involvement. And the coherent network EC can also reduce DMA traffic, which will further improve systems performance. That's why we feel in network EC is a promising technology to be adopted for EC service in next generation data centers. So the EC we propose in our work is a set of coherent EC primitives or APIs. Essentially, it has 3 different kinds of APIs. It exposes a set of flexible APIs for upper layer applications, such that the users can specify various parameters to meet their needs. For instance, users can specify what's the calculator, communication channels, memory layout, and how many number of receives this API should wait for. So this is the, in this table, this is the details of the in-EC APIs. So I just give one example of how to design receive EC send primitive on SmartNIC. In this API, once CPU issues one receive EC send request, RNIC starts to wait for remote chunks. And once the remote chunks arrive, RNIC ships all related data chunks from host memory to on-NIC buffer via our DMA operations. Then it performs EC or XOR operations on the local chunks and the received chunks. Finally, RNIC sends the computation results to other nodes. With receive EC send, we can reduce the number of CPU involvement and DMA traffic as well. So we implement our proposed in-EC and APIs within Mellog's Offload driver. So we successfully co-designed it with memory cache T, and we called it in-EC cache. Essentially, this is a key value store service. More details about this design can be found in our paper. We choose a set of figures from our paper to show how in-EC impact on percentile latencies. You can get more results from our paper. So look at this. When we look at these figures, we can see that with in-EC we are able to reduce percentile latencies by up to 77%, 66%, 62% respectively. Let's also take a look at the in-EC cache surface level performance. We ran YSSB workloads here. The end-to-end throughput numbers illustrated that in-EC represents an average performance boost of up to 57% with read-dominated workloads and an average speed up of 25% with write-heavy workloads. So we can see that in-EC can uniformly benefit state-of-the-art EC skins by offloading their computation and communication fully to the SmartNICs. So with this, let me conclude my talk. So in this efficient paper, we try to emphasize an important systems research direction on offloadable and migratable microservices on disaggregated data center architectures. We performed a survey on related studies and presented our vision and associated research challenges and proposed a research roadmap to achieve the envisioned goals. Our proposed research roadmap needs a lot of research work, innovations, and collaborations from the community to achieve these goals. Of course, we are looking for collaborations. With this, let me thank your attention. Please feel free to ask any questions if you have.